All right, so this is a continuation of the chapter 4 that I started before. Contingency tables and association is what I'm going to continue to discuss here to complete the chapter. All right, the goal of this section is to find technique, okay, to summarize relations between two qualitative variables. Remember that in the previous video, we dealt with quantitative variables, the relation between quantitative variables, and we talked about correlation coefficients and all the things you can do to check the relation between two quantitative variables. Here we are looking at qualitative variables. Okay. And I'm going to start it by example. Okay. So data information. A professor at the community college in Mexico conducted a study to assess the effectiveness of delivering an introductory statistics course via traditional lecture-based method, online delivery, no classroom instruction, and hybrid instruction, online course with weekly meetings. So the grades students received in each of the courses were tallied. All right, so of course, COVID-19 pandemic has brought a lot of discussion about what is the best for the student. Should we come face-to-face, put a lot of restriction, or we go online fully, or we combine these two? So this is a way to assess what is the best method for the student. All right, so these were tallied this way. Traditional, the student gets 36 student gets A, 52 student gets B. Online, 39 student gets A, 55 student get B, and so on and so forth. So the grades were recorded and tallied. And so we want to find the association. Okay, this table, when you present your data in this form, this is what we call contingency table or two-way table. It relates two categories of data. Okay, the methods and the grades. So that's why it's called two-way table or contingency table. The row variable is grade. So how many people get A in each method? How many people get B in each method, in all the methods? How many people get C in all the methods? That is the row variable. The column variable is the delivery method for traditional, online, and hybrid. All right. Each box inside this table is referred to as cell. So everything here is cell. Call it cell. Each of these is called cell. Now, how do we undo this type of table? First, we talked about marginal distribution. Marginal distribution of a variable is a frequency or relative frequency distribution of either the row or the column variable in the contingency table. All right, so we should keep that in mind. Marginal distribution can be frequency or relative frequency. So here is an example. The example we are working with, of course, find the frequency marginal distribution for the course grade and delivery method. Determine the relative frequency marginal distribution for course grade and delivery method. We're going to use this actually for something later on. So what does this mean? It's very simple. All we do, this is the table to find frequency marginal distribution. So all we do is to complete this table, when we add across the row, we put the result here. So 36 plus 39 plus 24, which is 99. That would be this total. The same thing here, 52 plus 55 plus 66, that would be 173. And if you do the same thing across 57 plus 68 plus 90, that would be 215. 46 plus 38 plus 41, that would be 125. 46 plus 54 plus 31, that would be 131. We sum across the row and then we sum across the column. So the first column, when we sum all these together, what we get is 237. If we sum all these together, what we get is 254. If we sum all this together, what we get is 252. And that is the contingency table. All we need is to just put all these numbers, the sum. And the total from each side should be equal at this point. So if you had from one side, either the column or the row, you will get 473. This is called marginal distribution. Marginal distribution for the cost grade and the delivery method. Now let's go to frequency marginal distribution. It's the same thing as we know it in what we have talked about in the previous video. So instead of the frequency, now we are going to divide by the total. So remember that we got 99 in this place, and the total we have here was 743. So now we are going to divide everything by that number. So this will be 99 by 743, and that would be 0.133. The next one will be 173 divided by 743. That would be 0.233. And if you do that across, the same thing you will get. So this is 215 divided by 743. I'm using the marginal distribution, the frequency marginal distribution we found in the previous slide. So that would be 0.289. This one will be 125 divided by 743. That would be 0.168. Then you have 131 divided by 743, which is 0.1176. You do the same thing across here. So remember, we had 233 here. We divide again by 743. That would be 0.319. This column, we have 254 divided by 743. That would be 0.342. The next one is 252 divided by 743. That would be 0.339. If you sum across, you should get 1 or approximately 1. Sometimes the approximation we have done may not make it to be very accurate, a little above 1 or a little below 1, but the idea is to get 1. All right, so that is what relative frequency marginal distribution will give us. What is more, this is called conditional distribution. So it lists the relative frequency of each category of the response variable, giving a specific value of the explanatory variable in the contingency table. Now, this is a little tricky because it's conditional. It's conditional, we have to condition the work based on a particular explanatory variable. All right, so for example, let's go back to the same example we've had. So construct a conditional distribution of cost grade by method of delivery. I'm going to come back to that later. Then comment on any type of association that may exist between cost grade and delivery method. Now, I just put the table here so that we have something we are referencing. This is what we got from the frequency marginal distribution. Okay, so construct a conditional distribution of cost grade by method of delivery. This is extremely important, by method of delivery. Everything will change if it's not. So what does that mean? That means we are going to treat method of delivery as the explanatory variable. And I'm going to let you see how we go about that. So method of delivery is our focus. So we are going to use method of delivery as our explanatory variable, is that we are going to consider the sum in the column, the sum over columns. So the first entry here for A will be, what is the number? The frequency for that is 36, and that will be over the sum over the column is 237, 237, and that will be 0.152. If I go down the line, this will be 52 over 237. That will be approximately 0.219. For C, that will be 57 over 237. That will be 0.241. 46, this is 46 over 237 equals 0.194. Of course, this is the same thing. 46 over 237 equals 0.194. Now, once I'm done with the traditional one, I go to the online and then use the total sum across the column there too. So that would be 39 over 254, which in this case will be 0.154. And the next one will be 55 over 254. That is 0.217. 68 over 254. That will be 0.268. 38 over 254. That will be 0.150. Lastly here, 54 over 254, that will be 0.213. Now, when you go to the hybrid, again, you need to use the total across the column. We are doing this because we have this instruction by method of delivery. That's our explanatory variable, okay? So for this will be 24 over the total sum across the column there is 252, which if you use your calculator, you get 0.095. The next one is 66 over 252, which will give us 0.262. The next one will be 90 over 252, which will be 0.357. And then we have 41 over 252. That will be 0.163. And lastly, we have 31 over 252. That's 0.123. If we sum across the column, we should get approximately 1. Okay. And this is what we call conditional distribution. Right. And what I just want you to be careful about is this method, is this condition that we have to go by the method of delivery. I'm going to give another example that talks about that, give a different scenario. Okay, so comment on any type of association that may exist between the cost grade and delivery method. Again, this is exactly what we obtain. I just copy the answer here for the contingency for the conditional distribution. What can we say? First, for traditional, if our passing grade is ABC, right? So D and F is fail. So let's look at which one gives more, which one gives more passing, which one do we prefer, the students we pass the class. So for traditional A, B, C, A, B or C is just the sum of all these three. That gives us 0.612. For online, the sum of these three, that gives 0.639. So that's the proportion of those who passed. And for hybrid, that gives 0.714. So clearly, hybrid is preferred. It appears that students in the hybrid course are more likely to pass than the other two methods because we have higher proportion. So this is about 71.4% of the students in the hybrid class pass the class. So you can see how we can make use of this conditional distribution to come up with a lot of information. This is very very common in industries, in companies, people dealing with data, companies always having to do with different variables, different products, different things that they can consider this way. All right, so when we now want to draw a bar chart, because bar chart will give us a very good view of what is going on. Of course, conditional distribution, because we are considering three different, we are considering method of delivery, that will be the distinct colors that we are going to have. So for grade A, this is what we see in comparison for B and for C and for D and for F. We can easily see the bar and make comparison. Okay, and in most of them, even though for the hybrid, many people didn't get A, but many people got B compared to the others, and in C, many people. So it seems to be good. All right, I want to give another example just to see a different view. In a recent Harris poll, a random sample of adult Americans, 18 years and older, was asked, given a choice of the following, which one would you most want to be? So results of the survey by gender are given in the contingency table here. Actually, this is a frequency marginal distribution. So just to save us headache, I don't want to start from there. I want to focus on conditional distribution, frequency conditional distribution. So 144 females said they would like to be smart. 159 said they prefer smart, and so on and so forth. So we have smarter, younger, richer, and thinner. I want to make sense of this table, okay? So first, construct a conditional distribution of desired trait by gender. That is, treating gender as the explanatory variable. This is extremely very important, okay? Because remember before, if we go by the previous example, we were to treat what they want to be, this characteristic here. That was what we used as our explanatory variable before. In this case, we are treating gender as the explanatory variable. We are treating gender as the explanatory variable. That is just to make an emphasis here. And I'll show you what is the difference. All right, so then we comment on any relation between desired traits and gender. Okay, so let's move on to what we need to do. I bring the table forward because we will actually need those values when we are doing the computation. All right, so remember that before we were using column sum, okay? In the previous example, we're using column sum. In this case, because our explanatory variable is by gender, we are going to be using row sum. So we are going to consider these two numbers. That's the focus now. So if I want to find the relative frequency for this guy, that would be 144 divided by the total sum here, which is 1042. And if you do that, you are going to get 0.138. And if I go to the next one, that will be 81 over 1042. If you use a calculator, you get 0.073. The next one will be 425 divided by 1042, which should give you 0.408. The next one, the thinner, is 300 divided by 1042. That should be 0.288. And then none is 92 over 1042, which will be 0.088. Now, when we move to the male, 159, then we are going to consider this one here. We're going to consider this total sum. So that will be 159 over 1120, which will give us 0.142. The next one is 181 over 1120, that will give 0.162. The next one will be 520 over 1042, that will give 0.464. And next one is 158 over 10. I'm sorry, this shouldn't be 1042. This is 1120. This is 1120, and that should be 0.141. The last one here is 102 over 1120, which is 0.091. If you sum to the side, you approximately 1. I decided to put this example in order to distinguish, to make students see why this condition is extremely important. If we are to go by the characteristics of smarter, younger, richer, and thinner, we will have to consider the sum across the column. Here we are considering the sum across the row. Okay, so let's go to the second part. So I just bring this table back here. It's exactly the numbers we got before. So how do we comment on this? First, an American adult who most want to be richer is slightly more likely to be male than female. So richer is most likely male than the female. 0.46 is a little likely. Okay, so this is very good to see the proportion. So an American adult who most want to be thinner, okay, is more than twice as likely to be female than the male. So thinner is 0.141, is more than twice want to be thinner for female. So female want to be thinner, that's what happens. Why an American adult who most want to be younger is more than twice as likely to be male. So male want to be younger more. The female, this is more than twice actually. An American adult who most want to be smarter is nearly equally likely. Okay, so being smarter is almost the same. So both female and male want to be smarter. Meanwhile, male want to be younger than female, and female want to be thinner than male. Those are the conclusion we can draw from this. And again, if we want to put, remember in the previous example, when we want to draw the bar charts, we use our legend is traditional, online, and hybrid, because that is the condition. In this case, our legend will be female and male. So we have to draw bars representing each of smarter, younger, richer, and thinner, and none for female and for male. So I decided to put the bar chart here. So one set is for male and the other set is for female. We can easily compare what is going on, where the colors are given for each characteristic. All right, before I close, I just want to talk about Simpson paradox. This describes a situation in which an association between two variables inverts or goes away when a third variable is introduced to the analysis. If, for example, we are considering smarter and thinner, and suddenly we say we want to talk about something like younger or richer. By the time we introduce the third variable, we discover that the association is no longer what it used to be. In that case, we say we have Simpson's paradox. And this will be the end of chapter 4. I hope you enjoyed this video. Leave me comments if you have any questions. Always leave the comments, and I will see you in my next video. I'm going to be talking about probability. Probability will be the next topic of discussion. That will be chapter 5 of the book we are using. Thank you very much, and have a wonderful day.